Okay, welcome again, guys, to another G Squared Academy video where excellence is epitomized. I thank you guys for all the likes, shares, subscribes, comments, everything that you guys are doing. I really appreciate that. Keep sharing the videos, keep liking the videos, keep commenting on the videos because I appreciate them. All right, so today we're going to be getting into this business of redox equilibria. Okay, so that's what we're going to be looking at today, redox equilibrium. And this is really for CAPE or A-level studies. Okay. Equilibria. So here's the situation, right? If I have a metal, and well, before we even get there, just remember that equilibrium has to do with this dynamics between species that are changing from one thing to another and then back into that thing. Okay, so the equilibrium that we're looking at really is a equilibrium which is expressed between metals. So you can have a metal, right? And it's metallic ions, Mn plus. Okay, so that's one way you can get an equilibrium, or you can get equilibrium with variable oxidation state species. So I have a species which is already in an oxidation state. It could be positive or negative, right? And it can change to another state, which is positive or negative. So you can have your metal, and the metal converts to a metal, an ionic species, and you have the equilibrium being established between these things. So you really should have equilibrium arrows instead of these arrows, right? Or you could have an equilibrium being established between a species, which is already charged, an ionic species, with another ionic species. So this is the equilibrium that is being established, right? So what happens really is that if it is that I were to place a metal, for example, in a container of ions of that metal. So let's say I have zinc, yes, and I place that in a solution of zinc, 2 ions, zinc nitrate, for example. A number of things can happen. One of those things is that zinc, the metal, can dissolve to form zinc 2 plus ions, or the zinc 2 plus ions could actually become reduced to form zinc solid. So what we observe really is that the first situation happens where the zinc solid is converted to the zinc 2 plus ions. All right. It would be interesting to determine the charge for this process. To occur, but we cannot do it with just zinc by itself. And this zinc system is what we call a half cell. So we would need to add another half to make it a whole. And so what we could do is let's just hypothetically say we connect it to a copper system. So over here we have our copper, right? And this is copper 2 solution. Yes, so Cu2 plus solution, and this is your copper solid. Yes, and we connect this to a voltmeter, right? We connect that to a voltmeter, and we connect that to the zinc over here. And this is zinc solution again, and this is your zinc solid. Yes, and of course, what we're going to do is we're going to connect it via this thing called a salt bridge. If I could just double that line, there you go. Right, so we connect that by a salt bridge. When this happens, what we recognize now, we find that there are some observations occurring in either half cell, over here or over the other side. Something is happening here and something is happening over there. Now, this cell is what we call an electrochemical cell, and it shows, well, the potential difference for reduction or oxidation to occur in either cell. And so observations are made as to what happens in each cell. And what can happen here is that the observations would indicate what is reduced or oxidized. And so therefore it tells us which of these two things, zinc or copper, is a stronger oxidizing agent or a stronger reducing agent, really. In this case, it doesn't really matter. Now we can actually denote this cell, or we can write it in shorthand in a certain way. So let me just clear all drawings here. What we could do is write it shorthand. Instead of drawing all of that, what we could write is Cu2 plus aqueous, right? And then this is actually a phase boundary between that and the metal, right? And then between that, we have what we call the salt bridge right there. And that is how it is denoted. And then you have your zinc, solid, and then you have a phase boundary between that to go into zinc 2 plus, which is aqueous. So we could actually write that electrochemical cell in shorthand like that. This doesn't, the shorthand doesn't show what is being oxidized or reduced necessarily. We would have to get that information from observations, from actually doing a practical, even though we can have standards as to how we write it. But it's better to get that information from observations instead of just writing it and saying, yes, this is where reduction occurs or where oxidation occurs. So this sort of cell only shows the possibility of these two reactions occurring, or the possibility of the reduction, oxidation between copper and zinc. However, it does not show us the reduction potential of copper by itself or zinc by itself, right? And so therefore, what has to happen is a standard cell, a standard electrode has to be set up for that. And that standard electrode is actually what we call SHE, the standard hydrogen electrode, right? And the standard hydrogen electrode is set up to determine the reduction potentials of different species. And the reason why it is able to do that, it's assigned a value of 0.00 volts. So any number that you get in reference to that would be the potential for that thing to be reduced or oxidized pretty much. All right. So the standard hydrogen electrode now, we can denote it as PT, which is a solid because we use platinum. It is a platinized platinum electrode, right? And the phase boundary there between hydrogen gas and the platinum. And the solution being used is actually 1 molar hydrochloric acid. So that is denoted as H plus aqueous, right? And then you have your phase boundary right there. So what's happening now is that we can compare the reduction potential of any species pretty much with reference to the standard hydrogen electrode. And so we can determine their potential to cause reduction. And that would give us a voltage reading on a voltmeter. Okay. Okay, so when all of that is done and we compare these different species to the SHE, standard hydrogen electrode, what we end up with is the electrochemical series, right? So we end up with the electrochemical series, which, as I've said before, shows the potential for a species to cause reduction in another species. Now, the critical thing about the electrochemical series is that the more negative the number, right? The more negative a number is, the more likely it is to cause reduction. Okay? So the more negative it is, the more likely it is to cause reduction in another species. All right? So the ones which are most negative would cause reduction. All right? Now, so these electrode potentials may be used to calculate the E naught of a cell. So you can be given a cell where two species are together and you have to calculate the E naught of that cell, right? And the E naught of a cell is equal to the E naught for reduction minus the E naught reduction minus E naught for oxidation. Okay, let me just put oxy for that one. Okay, so here's the situation now. When you are calculating the E naught, let me first denote, highlight that this E naught means it's done under standard condition. It's denotes standard conditions, which is 1 atmosphere or 101 kilopascals, right? That should be kilo pascals, 298 K. And solutions are 1 molar solutions. Okay, so the E cell denotes the E naught denotes the reduction potential of a cell under standard conditions. And so we can use those reduction potentials generated from the standard hydrogen electrode to calculate the E naught of any cell. All right, and that is pretty much what redox equilibria in terms of calculation is all about. Now, before we move on to get into the calculations, I just want to point out a few things about the standard hydrogen electrode, because your examiner may ask you about the purpose of the platinum and why it is platinized, etc., right? So the functions of the platinumized platinum electrode is that it is an inert metal. You do not want something that's going to be interfering with your process, something that's going to accept electrons or give up electrons. And so therefore, the platinum electrode provides an inert metal which does not interfere with your process. The second thing is that it allows, so the platinum allows hydrogen to adsorb to it. Okay, it allows for that. And remember now, if you remember your organic chemistry, that platinum is used as one of those catalysts for hydrogenation reactions, because hydrogen to it and can be split. The hydrogen bond can be split using that. That third thing now we want is it's that it's covered with finely divided platinum. And why would you want to do that? You try to do that to increase the surface area of the electrode so that equilibrium is reached much faster. Okay, so it's really just about the pace of the reaction there. So now that we have those things cemented, we understand where the redox equilibria idea comes from. We understand how the numbers are generated in comparison to the standard hydrogen electrode. We understand that we can use this equation, E cell is equal to E reduction minus E oxidation, to determine the E naught of a cell. Let us now do some calculations.